Good morning, everybody. Myself is YB Angadi, Assistant Professor in Chemistry, Government First Grade College, Elvarga. Today's session program is BSc, subject Chemistry, 4th semester, session 2nd. Topic coordination compounds, in them Werner's coordination theory and experimental verification of Werner's theory. We already known in the previous session existence of the coordination compounds, formation of the coordination compounds, definition of the coordination compounds are known. Compounds having at least one complex ion in it. Complex ion containing compounds are called the coordination compounds. In 1893, Werner put forward the famous theory of coordination compounds to explain the structure of complex compounds and also properties of the coordination compounds and how form the coordination compounds. Hence, Werner's is rightly called as the father of the coordination chemistry. First introduced such a type of the compounds. Hence, this theory is said to be Werner's coordination theory. Werner coordination theory. In his work, the Nobel Prize in Chemistry 1913, in the recognition of his work on the linkage of atoms in the molecules, by which he has thrown new light on earlier investigations and opened up a new field of research, especially in the inorganic chemistry. New type of the synthesis were done by using such a type of the compounds. Werner coordination theory is one of the milestone in the formation of a new type of the inorganic compounds called the coordination compounds or complexes. He given a theory, Werner, called as the Werner's coordination theory, by using certain postulates called as the postulates of Werner's theory. Let's consider these postulates of Werner's theory. According to Werner's postulates, in coordination compounds, the metal atom exhibits two types of valencies. Like primary valency and secondary valency. Every coordination compound is there. There must be presence of the central metallic ion. That means one metal atom. This metal atom exhibits two types of valency. Two types, not a number, types. One is a primary valency and another one is a secondary valency. These two valencies are, one is a primary and another one is a secondary valency. Two types of the combining capacities, two types of the mixing ability of the metal atom. The primary valence is ionizable and non-directional, whereas the secondary valence is non-ionizable and directional. Primary valence, one type of the combining capacity is there, that is ionizable, charged character, usually positive character, ionizable, and non-directional, interaction between other entities, not any fixed direction. Whereas the secondary valence is a non-ionizable and directional. Secondary valence also exhibited by the metal, it must be certain fixed direction, like as covalent bonding. We know in the covalent bonding, directional characteristic properties. Orbitals are arranged in the space with a definite geometry, definite shape, definite direction. They gives the definite shape. Same way, these secondary valencies are arranged in the space. These are directional, fixed directional. And in modern technology, the primary valency corresponds to oxidation state and the secondary valency corresponds to the coordination number. These primary valency in the sense oxidation state of the central metallic ion. We know already oxidation state, how many number of the electrons utilized for the bond formation, how many number of the electrons lost, how many number of the electron gains. This number, oxidation state of the central metallic ion. That means central metallic atoms exhibits one fixed oxidation state, one kind of oxidation state. And also secondary valency corresponds to coordination number. In later class, we will consider what is meant by coordination number. Coordination number in the sense number of the coordination bonding around the central metallic atoms in the complex ion. How many coordination bonds are formed. So certain number of the coordination bonding around the central metallic atom is the one type of the valency, and another type of the valency is the oxidation state of the central metallic ion, like two types of the valency. For example, simple salts are considered only one type of the valency is possible. For example, NaOH, Na plus and OH minus. Na exhibits only plus character. CaCl2. Ca plus 2 is the one kind of plus 2 oxidation state. Carbon valency tetra valency of the carbon 4 combining capacity, only one type of the valency. But here in this coordination compound, central metallic atoms exhibits two type of the valency. One is a primary, that is oxidation state, and another one is a secondary valency, that is coordination number. Two types of the mixing ability by the metal atom. This one postulation, very important properties by the central metallic atom. It must exhibit two types of the valency. One is oxidation state, another one is a coordination number. For example, in the cuprammonium sulfate example is considered, we know this one is a coordination compound because it undergo ionization, it forms the CuNH3 plus 2 and SO4 minus 2. Here central metallic atom by copper. This copper exhibits two type of the valency. One is oxidation state. Here plus 2 is the copper, plus 2 oxidation state is there. Copper exhibits the plus 2 oxidation state. Secondary valency, copper binding with the 4 ammonia molecule. 4 ammonia molecule, 4 ligands around the copper, 4 coordination bonding around the copper is another kind of the mixing ability. One coordination bonding, here ionic bonding. Single metal exhibits the two type of the mixing ability. One is oxidation state and another one is a secondary valency, that is a coordination number, or primary valency and secondary valency. Any matter in the coordination compound exhibits two types of the valency. One is a primary and secondary, or oxidation state and coordination number. In this example, K4 FeCN6, K4 is the simple ion. FeCN6 minus 4 ion is the complex ion. In this complex ion, iron acts as a metal atom. It exhibits the oxidation state, one of the capacity of the electronic exchanging character, electron loss character. Iron atoms exhibits the plus 2 oxidation state in this molecule, and also having a secondary valency. 6 cyanide ion binding with the iron, coordination bonding is there, hence the secondary valency is 6. Iron exhibits a primary valency plus 2, secondary valency 6. Two types of the valency exhibited by the iron. Like any type of the coordination bonding is there, coordination compound is there, there must be central metallic atoms exhibits by the two type of the valency. One is a primary and another one is a secondary valency. This is one of the first postulates of Werner's theory. Let's consider second postulates of Werner's theory. Every metal has a fixed number of secondary valencies. Central metallic atoms exhibits by the two type of the valency, primary and secondary. But one condition is there: every metal has a fixed number of the secondary valency. Fixed number, 4 coordination number, 6 coordination number. For example, copper is taken, usually 4 coordination number is a common, fixed. Iron is considered, 6 coordination number is usually fixed. And cobalt is considered, 6 coordination number is fixed. It has a fixed coordination number, fixed secondary valencies is the postulates of the Werner's theory. And in the third postulate, let's consider third postulates of Werner's coordination theory. It has a two type of the valency. One is a primary and secondary there. This metal atom tends to satisfy both the primary as well as the secondary valency. Satisfied, binding. What the character is there, that character is satisfied. What character? Combining capacity character, valency character, primary valency character. This primary valency character satisfied. And also the secondary valence also satisfied. Primary and secondary valencies are satisfied in the central metallic atom. Primary valence is satisfied by the negative ions. Positive oxidation state by the central metallic atom, it has a positive oxidation state, primary valency. It must be satisfied by the presence of the anions in them. There must be need of anions. What the number of the cationic oxidation state by the metal is there, it must supplied by the negative anions in the molecules. Whereas secondary valencies are satisfied by ligands. Ligand secondary capacity is there, coordination number capacity is there, coordination bonding capacity of the central metallic atom is there. This one is satisfied by the ligands, suitable number of the ligands. These may be neutral ligands or negative ligands. What the type of the ligands? It has a capacity of the donation of the lone pair of the electron. Donor atom containing molecules are needed. Hence only satisfied the secondary valence by the metal. Secondary valence of the metals are satisfied by the ligands. There must be ligands needed. So hence in the primary valency satisfied by the anions in the molecules, secondary valency is satisfied by the supplying by the ligands. These two must be supplied. For example, in the C1H3,4SO4 molecule, plus 2 is the primary valency and 4 is the secondary valency of the copper. Copper exhibits the two type of the valency. According to third postulates, this plus 2 valency is satisfied by the anions because SO4 minus 2 is the anion. This SO4 minus 2 is binding with the plus 2 of the copper. 4 valency, coordination bonding capacity of the copper 4 is there. This must be satisfied by presence of the 4 ammonia ligands, 4 NH3 molecules. Similarly, in this molecule, K4FeCN6 molecule, plus 2 is the primary valence of the iron, satisfied by the Cn minus. Among these 6 cyanide, 2 cyanide ligands compensate the positive character of the iron plus 2. Similarly, 6 secondary valence of the copper satisfied by the 6 Cn minus ions. 6 cyanide ligands. Cyanide ligand binding is there one kind of the bonding. One kind of the bonding is the coordination bonding. All 6 ligands binding with the central metallic atoms with 6 coordination bonding. 6 secondary valence is satisfied by the copper. So this secondary valency, primary valency, both are satisfied. In the fourth postulates let's consider secondary valencies of a metal arranged in a space to give a definite geometrical shape to complex depending on the number of the ligands. This one is also be important. Arrangement of the ligands around the central metallic atoms depends on the coordination number. Secondary valencies, how many number of the secondary valency, these are arranged, distributed in a space around the central metallic atoms, that gives the shape of the complex depending on the coordination number. Coordination number is a 2 is there, linear geometry. Coordination number 3, triangular. Coordination number 6, octahedral. Coordination number 4, square planar. Depends on the number of the secondary valencies around the metal. These decide the geometry of the complex. Hence, in this assumptions, in this postulates, coordination theory of Werner's, 4 important postulates are needed. Central metallic atom, it provides the 2 types of the valency. One is the primary and the secondary. Primary is ionizable and non-directional. Secondary is non-ionizable and direction. And primary valencies are arranged in the space. Primary valencies are satisfied by the presence of the anions in them. Secondary valencies are satisfied by the ligands. And definite number of the secondary valencies, and these secondary valencies arranged in the space to give the definite geometries. For example, according to Werner's theories, consider this molecule CO NS3 6Cl3. Primary valency cobalt, it has a +3 valency. Primary valency is satisfied by the Cl3. This supplied the 3 minus ions. And 6 valency, secondary valency is satisfied by the 6 ammonia molecule. Hence this coordination sphere, and this one is an ionizing sphere. Consider the same example as a cobalt content. Here among the 3 Cl minus ion, 1 Cl minus is act as a ligand. One is a ligand. Ligand as well as a one ionizable character. Both character by the Cl minuses. Hence this type of the cobalt +3 is exhibits the +3 valencies, 2 here minus and 1 minus, total 3 is supplied. And 6 bondings, 5 are the amines and 1 is a Cl minus. So hence only Cl2, only 2 Cl minus get ionizable. Similarly, in this molecule also be presence of the 3 chloride ion, 4 ammonia ligands, 2 ligands of Cl minus act as a ligand character as well as ionic characters. Only 1 ion get ionization. So this, by using these examples, experimental verification of the Werner's theory is possible. He given the number of the examples, and by using the various experimental evidences, given the support of existence of the coordination compounds. Following evidences supports the Werner's theory. Validity of the Werner's theory, cobalt +3 ammonia complex. Given in a following is support by the chemical reactivity or precipitating of AgNO3, number of the chloride ions in terms of formation of the AgCl molecules. The number of the Cl minus ions precipitated are 3, 2, 1, 0 respectively. Consider this example. Here COCl3 6NS3, COCl3 5NS3, COCl3 4NS3, COCl3 3NS3. This can be written in the Werner's formulas. 3 Cl free ions, 2 Cl, 1 Cl, no Cl in the ions. This one is experimentally proved by using the test of precipitating test, that is AgNO3 test. Addition of the AgNO3, 3 chloride ions are precipitated. Addition of AgNO3 to this molecule, two chloride ions are formed. Only one chloride ions are formed. No chloride ions are formed. Experimentally proved. That means even though presence of the three chloride in this example, but no ions, free ionizations of chlorine is not possible. Hence, these are used as ligands. Experimentally, evidences are done by using the AgNO3 test. And another one test is there, measurement of the molar conductivity. Simply in the experimental determine the conductivity values. It gives the presence of the number of the ions. Conductivity experiment gives the number of the ions. Depends on the magnitude of the conductivity measurement, we can decide the number of the ions in them. In this example is considered experimental conductivity measurement experiments are considered. First example, it gives the molar conductivity 500 ohms inverse, 300 ohms inverse, 150 ohms inverse, no ohms, non-electrolyte, not a electrolyte, no conduction takes place because no ions in them, no any free ions in them. So this one is experimentally proved because even though presence of the three chloride ions, but these are used as a what the bonding is there in the what valency, secondary valency is there. Hence there is no any free chloride ions. So this one is also be experimentally supported by the Werner by using varieties of the experiment. So molar conductivity of the solution of the coordination compounds also helps to estimate the number of the ions in the solution. In the first example gives the 500 ohms, 4 ions. Second example 250 to 300 ohms inverse, presence of the 3 ions. Presence of the 2 ions in the third example 150 ohms inverse. And in the last example it may be noted that when the number of the coordination anions is the same as the oxidation number of the central cation, the coordination compound is a non-electrolyte. Oxidation state and what the central metal atomic oxidation state and anions are same. This one is said to be electrolyte. In the last example, cobalt exhibits a +3 and 3 anions. Hence, this gives the non-electrolyte. Experimentally proved by the Werners, and one of the important milestones to explain the coordination compounds. Hence, all these about the Werner's coordination theory. In this revision, postulates, 4 postulates, central atoms exhibits the 2 types of the valency, primary and secondary, and a metal has a fixed number of the secondary valency. And a third postulate is the metal atom satisfy the both the valencies, and secondary valency decides the what the geometry of the molecules. And experimentally, this can be verified by using chemical measurement as well as conduction measurement. It is possible to assign the existence of the coordination compounds. This is all about the Werner's coordination theory. In the next session, also consider further information about the coordination compounds. Thank you.